Alright folks, back here with another video looking at application of derivatives, where we are going to continue looking at the idea that the derivative is describing an instantaneous rate of change with a little different, we might say here, approach. Where we're actually going to look at some application here using that idea in sort of an implicit manner. Right? And we're going to be studying what are called related rate problems. Right? Let me go ahead and bring my notes up here. This is probably the best way to show you what I mean by a related rate problem is to actually open with some related rates. This is almost a related rate problem here. Again, I'm just going to highlight, to begin with, just a little bit of initial information, right? To begin with here, in a related rate problem, what you're often looking at is the rate of change and the relationship between the rates of change in relationships that exist between variables. All right. For example, with the circle here, I've gone ahead and drawn a circle here with a radius of 20 feet. And there is a relationship that exists between the radius of the circle and the circumference. Right? We understand geometrically that there is this relationship, and we understand geometrically that the circumference is always going to be 2 pi times my radius. Right? The distance around the outside, the perimeter of a circle, is called its circumference. Right? The perimeter of a circle is referred to as the circumference, and the circumference is always just 2 pi, 2 times the value pi, times the radius of our circle. So in this case of having a radius of 20 feet, the circumference is 2 pi times 20, or 40 pi feet. Right? And our circumference would be described right here. Now, that is not a related rate problem. That is a geometry problem, right? Where we are calculating circumference, right, using the radius of our circle here. What is going to make this a related rate problem is if we think about the relationship that exists between these two variables, right? Where in that relationship we're looking at the rate of change in C with respect to some other parameter. And typically that parameter is going to be the value of time t. And if we look at the rate of change in C with respect to time t, that's going to have some influence over the rate of change in the radius with respect to time t. And vice versa. If I was to consider changing my radius of this circle with respect to time t, that would have an influence on the circumference changing with respect to time t and that rate. All right. What we note initially here, let me bring this up into view. All right. I say consider the radius of this circle changing with respect to time. Right? With respect to a parameter of time. All right? The circumference of this circle is also going to change with respect to that parameter time. Right? If I change the radius of the circle with respect to time, the circumference is also going to change with respect to time. And I could illustrate that here. Let me see if I can do that. Bring this up. Let me go ahead and fade over into this. Yeah. Go ahead and scroll down here. Here I have a circle. right? Where I can change this circle's radius. Let me go ahead and scroll up just a hair so you can see this. I'm able to change this circle's radius by moving this slider. And as this circle's radius changes, so does the circumference, so does the distance around the outside of the circle. Right? And as the radius changes with respect to time, here I'm changing it rather slowly with respect to time, right? We could say 1, 1,000, 2, 1,000, 3, 1,000, 4, 1, right? That circumference is also changing with respect to those ticks of time. Right? Well, the relationship that relates the circumference of a circle to its radius, the relationship c equal to 2 pi r, contains within it a little bit of implicit information about how these two variables change with respect to each other for some other parameter, with respect to some other parameter. In this case, the parameter of time. We can consider thinking about, let me bring this back. So we're going to look here at this relationship, and we're going to consider allowing our circumference to change with respect to time. We might think of that as dc dt, or this value c prime of t. Right? And if I apply that operator to the left-hand side of this relationship, if I apply to c the operator d dt, right, then I have to also apply that operator to the right-hand side. And maybe I should note that here. Let's go ahead and throw in here. We're going to apply the derivative operator with respect to t to c. Right? Our description of circumference, which is going to be dc dt, right? Which is like applying the derivative operator then to the right-hand side, 2 pi r, where 2 pi r is going to be, what, a constant multiple, and we're just going to be applying that derivative operator to the value of r, where when applied to the value of r, just becomes the value dr dt. Where what is dr dt? Dr dt is the rate of change in the radius of the circle with respect to time. All right? So overall, right, I think we summarize this here. Yep. What we're able to say with this relationship right here, where all we've done is applied this derivative operator, right, to either side of the relationship for the circumference of a circle and the radius, c equal to 2 pi r, and obtain this relationship right here that says the rate of change in the circumference of a circle with respect to time is equal to 2 pi times the rate of change in the circle's radius with respect to time. Right? That dc dt is equal to 2 pi times dr dt in our relationship. And it is relating these two rates of change. This is where it gets the idea of related rates. Right? We're relating through the circumference formula for a circle, 2 pi r, we're able to obtain a relationship between the rates for dc dt, the rate of change in the circumference with respect to time, and dr dt, the rate of change in the radius with respect to time. All right. And here's the relationship. So if I know one of these rates, I can solve for the other. Let's bring this into view. So for example, if I have a radius of a circle and it's increasing at a rate of 2 feet per minute, That means dr dt would be equal to 2. And the rate of change in the circumference of the circle then would be described by 2 pi times that value of dr dt times the value of 2. The rate of change in the circumference of our circle with respect to time t would be 4 pi feet per minute. All right. When our radius is increasing at 2 feet per minute. All right. And we're able to describe that relationship using this related rate formula that we developed from the relationship between the circumference and the radius of a circle. Right? Now, you'll notice this does imply that there's a direct relationship between these two rates in this particular case, a direct relationship where our constant of variation is 2 pi. That's not always the case. The relationship doesn't always exist in a direct manner. Let's consider another case involving a circle. And let's consider the area of a circle. Right. We know it also depends upon our radius, such that the area of a circle is equal to pi times our radius squared. And this is a relationship that exists between the area of a circle and its radius. Right? If I have that circle of radius 20 feet, the area would be 20 squared times pi feet squared. So 20 squared would take me to 400. My area would be 400 pi feet squared. Pi is about 3.14, so 400 times 3.14 is somewhere over 1,200. Feet squared would be the area of our circle. Now, in this case, however, we're going to be interested in what is the rate of change in the area with respect to time t in terms of the radius. Right? And we can use this relationship to determine this. Assuming dA dt is equal to a prime at t, which describes the rate of change in the area of the circle with respect to time t, I can apply that derivative operator d dt to the value of a on the left-hand side of this relationship, which means I would apply it to the right-hand side, where when applied to the right-hand side, this value of pi is going to be a constant multiple, and it's going to factor itself out of the application. And we're going to be left with finding the derivative with respect to t for the value of r squared. Where here you want to note what you have is an implicit derivative calculation. We're asked for the derivative with respect to time t, where what we have and working with is a function of r squared. When we consider this derivative, we might want to think about r being some function of time t that's stated implicitly. It's going to help us calculate this. And remember, from implicit differentiation, we developed a rule that will help. And that basically said if we're going to find the derivative with respect to x for any function of some other variable, and maybe I should be using my dummy variable u. That was really where we spent a lot more time. All right. With respect to u, the derivative of x with respect to u is going to be u prime times the derivative of y with respect, that would be the derivative of u with respect to u for f of u, which would be du dx times du at, du of f of u, the derivative with respect to u for f of u. Recall this result, or this result here on the right-hand side, from implicit derivatives. Well, this r squared is our function of u. That's being, what? We're having the derivative operator applied to it with respect to t. So applying those implicit methods here, things do get a bit more elaborate. We have the derivative with respect to t for r squared, then must be r prime times dr. Careful there. Yeah, ddr of r squared, which would be the derivative with respect to r for r squared. It would be dr dt times ddr of r squared, where ddr of r squared is simply 2r. So it would be 2r times dr dt. That would be the derivative with respect to t for r squared. And if we substitute that into our result, we end up with dA dt must be equal to 2 pi r times dr dt. Where again, dr dt is describing the rate of change in the radius of the circle with respect to time t. Right? And I think I summarize it here where we say, note dA dt then is equal to 2 pi r times dr dt. The rate of change in a circle's area with respect to time t will be given by 2 pi times the radius times what would be the rate of change in the radius with respect to time t. Right? Not only does dA dt depend upon the rate of change in our radius with respect to time t, it also depends upon what is r at any particular moment in time. All right? A value of r that we might think of as being some function of time t. So we set up an example here where we say, well, if we're considering the radius of the circle to be decreasing at a rate of 3 feet per second, at the moment the radius is 20 feet, the rate of change in the area at this moment is going to be described by the following calculation. Right? It will be described by dA dt equal to 2 pi r times dr dt, where since at this particular moment in time the radius is exactly 20 feet, r would be equal to 20. And because the radius is decreasing at a rate of 3 feet per second, dr dt would be given by the value -3. -3 feet per second is highlighting a decrease in the feet of the radius per second by 3 feet. The negative highlights the decrease in this behavior. Substituting in those values for r and dr dt, we get the rate of change in the area with respect to time t with this description. If the radius is 20 feet and the circle is decreasing at a constant rate of 3 feet per second, right, then the rate of change in the area with respect to time t would be 2 pi times 20 times -3. Right? Well, 2 times 20 is 40. 40 times -3 is -120. Times this pi gives us -120 pi. Indicating that the rate of change in our area with respect to time t is decreasing because of the negative by 120 pi square feet per second. The statement seen here. Right? This is highlighting a second example of an average rated, or not average rated change, a related rate problem. Right? Where here we were looking at the relationship between the rates dA dt and dr dt for the area of a circle and its radius. For the rate of change in the area of the circle with respect to some parameter t is 2 pi r times the rate of change in its radius with respect to that same parameter t. Here we're using time as that parameter. We did something very similar initially with the circumference of our circle. And through the application of the derivative operator d dt to both sides of our relationship for circumference, we were able to determine that the rate of change in our circumference was always just 2 pi times the rate of change in our radius, both with respect to some parameter. Here we use the parameter of time, t. All right. These are called related rate problems. All right. They're problems involving examining the relationship between the rates in a, what we might say here, relationship that exists in the real world. Here, that relationship being the circumference of a circle and its radius, or the area of the circle and its radius. Again, these two previous examples relating to the geometry of a circle are examples of related rate problems. They're problems exploring the relationships between the rate of change in R, A, and C, the radius of a circle, its area, and its circumference, all with respect to some other parameter, which in this case we use the parameter of time t. All right. This is an example of a related rate problem. And in general, related rate problems are solved using the relationship between the variables in the problem, implicit differentiation, and information given in the problem at a specific moment of the parameter. Maybe I should add that there, of the parameter. It could be a moment in time, or it could be a moment of some other value. Maybe it's number of items produced in a manufacturing process. Maybe it's at the moment we've produced 600 items. Right? It's just a moment of a parameter. So, sorry, I had to take a little break there. We were looking at, developing some general guidelines for solving related rate problems. And one thing I did notice here is, I'm going to fix this. The first guideline I say here is develop a useful relationship between the variables in the problem. I probably should say develop any useful relationships between the variables in the problem and related to the problem. In some related rate problems, there's going to be more than one useful relationship, and we're actually going to see that in the following example here. All right, but in our previous problems, that would be when we developed our circumference relationship with the radius, where circumference is equal to 2 pi r, and our area relationship with the radius, where the area of a circle was equal to pi r squared. Right? Those were the two useful relationships that we used to explore the relationship of those variables with each other and some other parameter value, right, with respect to a change in some other parameter value. Right? But begin with, develop some useful relationships. Now, once you develop the useful relationships, you apply and evaluate that derivative operator, and you do this implicitly on either side of the equation, right? In general, as just this operator we would think of as d dt, where t is some parameter representing an independent variable in the rates of change. And it's typically the value of time, right? We can think about two variables changing with respect to time, the parameter of time, but it doesn't have to be necessarily time. It could be any sort of what we might say is parameter, some other variable that isn't necessarily in your initial relationship. But you would apply in an implicit manner this operator to both sides, and that's what we saw happen in the relationships that we had above for circumference and radius, and between area and radius. And we applied that operator in an implicit manner. We relied upon this implicit rule. Right? And we might even say here, let's copy that, and perhaps come down here and note, if we do take and apply that operator with respect to t for some function of u, it is going to be equal to u prime times du of f of u. Or it is going to be du dt times du times, well, du of f of u. Right? This being the more useful result. This showing us that rate of change in u with respect to that parameter t. Right? And actually, we might even consider just ditching that middle result and going with this here. Right? This being the useful application of that operator. When you apply it to any function of some other variable, here we say variable u, it is du dt times the derivative of that function with respect to that other variable. Right? So we might even make note of that here. And then with the information developed here, right, with the useful relationship developed and its derivative applied for the parameter, you want to then identify the given information in the problem, including any known and unknown variables and rates. And what you're going to often do is use the known pieces of information to solve for any of the unknown quantities. All right. And this is, again, very generic guidelines here, folks. These are best illustrated with a little bit of example. So let's do that here. Let's look at a case involving the relationship known as the Pythagorean theorem. Here we have a few variables in relationship with each other. Right? If A and B are the side measurements of a right triangle, right, and I should say that here probably, I was just noticing I don't have this, of a right triangle, right? And C is the hypotenuse measure. Right? If any of the side measurements were to change with respect to some other parameter, maybe the parameter time, at least one of the other side measurements would also have to change with respect to this parameter of time. Right? If any side measurement was to change with respect to some parameter, perhaps time, what would have to happen is one of the other side measurements would have to change with respect to that parameter time. Or you could even see both side measurements change, but at least one would have to change. All right? That's going to be our useful relationship. Now, if we apply d dt to both sides to just start to explore what would be the rate of change between those variables, well, for those variables and the relationship between them, applying d dt to the left-hand side and to the right-hand side of this Pythagorean theorem, this relationship given by the Pythagorean theorem, that derivative operator is going to distribute itself across the a squared and the b squared on the left-hand side across the sum. And we saw, like above, when applied to a squared, it's going to become the derivative with respect to t for a times the derivative of a with respect to a, which would be 2a. When applied to b squared, it'll be the derivative of b with respect to t times the derivative of b with respect to b, which would be 2b. And we see a similar result here on the right-hand side for c squared. It would end up with 2c times dc dt, where dc dt describes the rate of change in the hypotenuse measure with respect to time t. dA dt describes the rate of change in side measure A with respect to time t. And dB dt describes the rate of change in side B with respect to time t. And this is a relationship relating all of those rates, those instantaneous rates of change, together in the relationship between the side measurements of a right triangle and the hypotenuse measurement. Right? And with this relationship developed, we can solve any problem, right, that relates those rates to one another. We can solve any related rate problem involving these three variables for the side measurements and hypotenuse measure of a right triangle, if we have enough given information. That's always kind of the key. So these do have to kind of be set up for you. You have to be given enough information. It's kind of like the area problem earlier for the circle. We had to not only know the radius at the rate at which the radius was changing to find the rate in the circumference, the rate of change in the area with respect to time t. We also had to know specifically a particular moment that the radius was at a certain measure to be able to calculate that rate of change. So same thing here. We have to be given enough information, right, to be able to solve these problems. Now, in a right triangle, assuming side A is always the square root of side B, so that A is always equal to, well, the square root of B, and we assume dB dt then indicates assume dB dt indicates that side B is decreasing at a rate of 5 centimeters per minute, right? In the above relationship, dC dt can be determined at the moment B is equal to 16 centimeters. And an illustration of this triangle at this moment is given below here. So here what we have is we do have some assumptions to begin with. We do have, in this case, side A is always the square root of B. So if B is 9 units, A is 3 units. Or in this case, if B is 16 units, A is 4 units. A is always the square root of B in this case. And we're going to assume that the rate of change in side B, here side B is being measured along the horizontal axis. It's this length of the base. If it was to decrease at a rate of 5 centimeters per minute, if it was to get smaller and smaller and smaller at that rate, the rate of change in the hypotenuse with respect to time t can be determined At the moment, side B measures exactly 16 centimeters. Right? Let's see how that is done in the problem below. Now, it does begin by noting, right? At the moment, side B is 16 centimeters. Side A is equivalent to 4 centimeters. And side C itself would be equal to the square root of 16 squared plus 4 squared. It would be the square root of 256 plus 16, or the square root of 272. It would be 4 root 17 centimeters in length. When B is 16 centimeters, when this distance here is 16 centimeters, and this distance here is 4, this distance here would be 4 root 17 centimeters in length. The hypotenuse would be. Also, dB dt would be equal to negative 5 centimeters per second, because we are decreasing at that rate in our problem. As for the rate of change in the side A measure with respect to time t, since A is the square root of B, this implies that if I apply the derivative operator with respect to t to that relationship, I get the relationship between the rate of change in my side measure A with respect to t in terms of the rate of change in my side measure B with respect to t, where the rate of change in A with respect to t is 1 over 2 root B times the rate of change in B with respect to t. Because when I apply this derivative operator to the square root of B, it is going to be dB dt times the square, the derivative with respect to B for the square root of B, which is 1 over 2 root B. And this becomes the relationship between dA dt and dB dt. So if I know dB dt is decreasing at 5 centimeters per second, and I substitute in negative 5 here, I know dA dt would be equal to negative 5 over 2 times the root of B. And it would depend upon the size of B. Now, if B is 16 centimeters, this would be 2 times the root of 16, or 2 times 4. And we'd end up with negative 5 over 2 times 4, which would be negative 5 over 8. And I do believe that is what we say here. Yeah. So if dB dt is negative 5 centimeters per minute, when B equals 16 centimeters, the rate of change in side A with respect to time t then would be 1 over 2 root 16 times negative 5, or negative 5 over 8. The root of 16 is 4 times 2 is 8. That's where we get the 8 in the denominator, and then negative 5 times 1 is negative 5. Right? If side B is decreasing at 5 centimeters per second, at the moment, side B is 16 centimeters. Side A is decreasing also at a rate of 5/8 of a centimeter per minute. Right? When side B is behaving in the way it is, at the moment, B is equal to 16 centimeters. So this becomes our measure of dA dt, where we already know dB dt is equal to negative 5. So if we take that information and we substitute that into the relationship we had developed from Pythagorean theorem, right? When B is 16 centimeters and dBt is negative 5 centimeters, this dBt becomes negative 5. B becomes 16, right? We see that happen here. We've seen that A is going to be 4 units, and dA dt is going to be negative 5/8, right? Indicating that the side A is decreasing at 5/8 of a centimeter per minute. And all this is going to equal 2 times C, where when A is 16 centimeters and when B is 16 centimeters, A is 4 centimeters, leaving C to be 4 root 17 centimeters from the Pythagorean theorem. And the only unknown we're left with in this relationship is dc dt, where we can use this given information from above and this acquired information from our work to now be able to solve for dc dt, the rate of change in the hypotenuse measure with respect to time t. And if we solve for that dc dt by dividing 2 times 4 root 17 on both sides, and then simplifying that statement, we will get negative 165 divided by 8 root 17. Simplifying the numerator into negative 165 and the denominator into 8 root 17. Now, I do believe we could rationalize the denominator on that, but that's not our biggest concern. All right. If we go ahead and make that into an approximation, this would indicate that the hypotenuse is going to be decreasing at about 5.002 centimeters per minute, when side B is decreasing at 5 centimeters per minute, and side A is always the square root of side B. And this is all at the moment side B is equal to 16 centimeters. With that given information, we can solve this related rate problem for dc dt. Right? These are tricky problems, folks. It's going to take a little bit of practice. It's going to take working more than just 2 or 3 examples like I've done here in the notes. These are puzzlers. These can be puzzlers. Some are very simple. Some are rather complex and involve a lot of, and I know it's, I guess, a bad pun, a lot of implicit information, a lot of hidden information in the problem that you're going to have to negotiate in your calculation, right? That you're going to have to navigate like we had done in this previous problem. It didn't look like we were given a lot of information there to begin with in this problem. We know that we were dealing with a right triangle here, where from Pythagorean theorem, a squared plus b squared must be equal to c squared. We were also told that side A is always equal to the square root of b, and that side B was decreasing at a rate of 5 centimeters per minute. And we became interested in what was the rate of change in side C with respect to time t at the moment side B was 16 centimeters. And with this little bit of given information and knowledge, we were able to solve for dc dt at that exact moment. Right? Using the relationship between A and B to find A, and once we had A's measure, we could say what C measures at this particular moment using Pythagorean theorem. And with the relationship between A and B, we can explore the relationship between A and B with respect to time t and their change with respect to time t, which will allow me to look at the rate of change in A with respect to time t with that information about B. And once I have information about A and B's rate of change with respect to time t, I can use that in the formulation we developed initially up here, along with those measures for side A, side B, and side C, right, to solve for this measure of dc dt. This is called a related rate problem. Right? These are all solved in general using these guidelines above. you develop a couple of useful relationships between the variables in the problem. Down here, that was our Pythagorean theorem was a useful relationship. And the other useful relationship was this one right here, where a was equal to the square root of b. These were two useful relationships in our problems between the side measurements of a, b, and or c. Develop those first, or acknowledge them. We then applied the derivative operator with respect to our parameter t on either side of those relationships, where we followed this generic implied derivative, rule, this derivative for this implicit function, where this was equal to du dt times the derivative of our function with respect to u, our function of u with respect to u. We did that with each of the terms here on the left-hand side and with this term here on the right-hand side. That's where we got these two terms on the left-hand side of this relationship for the related rates and this term on the right-hand side. And this is how we work through determining dA dt in terms of b. We applied that derivative operator to both sides of that useful relationship. And we found that dA dt was equal to 1 over 2 root b times dB dt. Right. We then, with the given information in the problem, including these knowns and unknowns that we developed, right, using the known side measurements to find the unknown side measurements, like side C from A and B, we use the known pieces of information to solve for any unknown quantities. And here we used all these known bits of information that were either explicitly or implicitly given to solve for dc dt, right? That unknown quantity in the end. These are related rate problems, folks. All right. Again, it's going to take practice, folks. That's really the only way you get better at these, is testing yourself, starting off with some simple cases and working your way up through the tougher ones. Kind of like I did here, starting off with circumference, and then looking at area of a circle, and then coming down here and looking at Pythagorean theorem that involves a relationship between more than two variables. Here, the three side measurements of a triangle. Yep, this is related rate problems, folks. And again, I'll show you a few examples in class, and you know, it's going to go back to just a little bit of practice, or a lot of practice in some cases. But with that said, that kind of wraps up our application of derivatives when looking at related rates and rates of change. What we're going to come back to is using derivatives to help us go a little further into functional analysis, and how to use the derivative calculation in a functional analysis, being able to look at a function and be able to begin taking our analysis procedure that we might have from algebra further with our knowledge of slope. That's all for the next videos, folks. Next few videos, what I plan to have here is we're going to talk critical points. We're going to talk intervals of increasing and decreasing. We're going to talk intervals of concavity. We're going to talk absolute extreme values. And we're going to talk local extreme values. So there's 5 topics there that go into what this concept of functional analysis. And then we might even put them all together into a 6th video, and then see how they all can be used in optimization problems. All right. So there's like 7 related videos to come here, folks, all working with functional analysis and optimization, right? Working towards developing techniques to solve what we call optimization problems. But I'm at 50 minutes and I should just shut up and make that next video. So I'll do that, folks, and I'll see you in the next one, and I'll stop there.